Hi, and thank you for joining. I'm very excited to talk about engineering for trust and peaceful sleep, which are two of my favorite things, and I think they're greatly needed these days, perhaps even more so than ever. My goal today is to tell you some stories and share some lessons learned from trying to prioritize these 2 points on the day-to-day job. My name is Ingrid, and I am a senior engineer on the traffic and delivery team at Netlify. For those of you that don't know Netlify, we are a platform for accelerating building, deploying, and testing modern web applications. And I want to take a minute in the beginning of this talk to give you a bit of context on our scale to better understand some of the examples that you will encounter. A lot of people think of Netlify as a globally distributed CDN that serves static content. But in reality, Netlify Edge is way more powerful than that. We support pre-rendering and compressing pages. We've actually just released throttle compression, which is pretty cool. You can redirect and rewrite with only 3 lines of code. We support automatic atomic deploys and rollbacks. And what that means is if you have a deploy from, say, 2 years ago, you can actually roll back to it if you choose to do so. You can also use serverless through what we call Netlify functions, which is built on top of AWS Lambda. So that's quite a bit of functionality. But what we're mostly proud about is being able to support more than 900,000 developers and businesses. And a pretty cool fact that I've learned recently is that 12% of internet users visit a Netlify-powered website per month. So if you think of it, we are quite literally powering a percentage of the internet, which is a job that we would like to think we take very seriously. And with that, two of our top priorities are trust and stability for our platform, but especially for our customers above everything else. Reliability for us means that if we screw up, businesses are offline. And we really hate the idea that a developer would be paged in the middle of the night because Netlify is offline. And if there's one thing that will always threaten to shatter good sleep and stability, it's usually complexity. Now, complexity is a very vast subject that comes from control theory, so says Wikipedia, and that you can spend many, many hours studying and talking about. There's things like our interview friends, time and space complexity. There's fancier terms like cyclomatic complexity, the number of linearly independent paths throughout a program source code, which is quite the tongue twister. But complexity also depends on size, it depends on number of contributors, it depends on the scale, so you kind of get the idea. But more important than this theory, we all know what it feels like dealing with it. It's a bit like this, just incredibly, mind-numbingly frustrating, just incredibly, incredibly frustrating. And it becomes even weirder when you realize that actually a lot of this is self-inflicted complexity pain, because a lot of it is down to human decisions. And I guess with that realization, it's time to drink or eat ice cream or both, just to feel a little bit better. But it's also why there's usually a lot of work done trying to contain the impact of that complexity and trying to improve it. And this idea of doing less or choosing boring, more simple technology has been a widely discussed topic to the point where it became a bit of truism. And it's kind of relatively straightforward to figure out how we got here. Do less better could be a response to complex systems failing in complex ways, and us as engineers trying to gain a bit more control. But especially when we're talking about engineering for resilience, engineering for reliability, doing less is an incomplete story, and it's not always possible. So let me give you an example of that. As I said earlier, if Netlify is down, our customers' production sites are actually down as well. It's not just that people are unable to use Netlify, businesses are unable to run. We run on the cloud, so very early on, depending on the availability and reliability of a single cloud provider was something that we identified as a risk that we were not willing to undertake. So enters MultiCloud. MultiCloud is a bit of controversial decision, and there's different opinions about it. We currently run on top of 6 different cloud providers, and there are a couple of reasons why we decided to do so and why it makes sense for us besides reliability. Most notable ones is that we are able to serve content from a location that is closest to you, thus giving users a better experience. But also that the vision for Netlify as a platform is being cloud agnostic. That means that we are not limited, we as engineers are not limited to a particular set of technologies, and we can afford to be a bit creative if we choose to do so, if it makes sense. Obviously, everything with being very deliberate. It also means that in the face of a major outage from one of our providers, anywhere in our network, Netlify service would automatically continue with minimal interruption. Our origin servers can swap between providers with no downtime. And if you're curious about how we did it, I linked the blog post in the slides, and you can read more about the nitty-gritty details. And you might have noticed that the date of the blog post is 2018. That was the date when we migrated all the origin servers, and at the time, our edge nodes were already operating in a multi-cloud setup. So we recognize that this was an important point of failure for us from relatively earlier on. And the reality is that the earlier you do it, the easiest your life is going to be down the line. So at the moment, because of we have all that foundation set, adding a 7th cloud provider, if we choose to do so, if it makes sense for our business, would be a known process. So mitigating core known points of failure early on is definitely can be a very strong plus. So the point of this example is that not all that would qualify as complexity is necessarily automatically bad. There are situations where adding extra guardrails, adding extra services would strengthen the reliability story and benefit both engineers and users. So in a way, we can look at it as being almost necessary complexity that was very deliberately added. But more often than not, complexity is not a deliberate decision that you've scheduled or that you can schedule. When you're, especially in a fast-growing environment, a lot of that growth eventually complicates the problem space. Even more so if you happen to run a multidimensional, non-deterministic system, which is the case of our platform. So some of the earlier decisions that we've made can in time become really painful. And the best example of that is looking at our deploys and the variation not only in types, but also in sizes. While 55.5% of our deploys are relatively small, between 1 and 100 pages, we also encounter some very large numbers, from 10,000 files all the way to over 1 million. This was a statistic from the last 30 days, where you can see that we actually have builds that are over 1 million files. And when you're trying to store and serve a large number of files, every bit of computation ends up adding up. And obviously, our goal is for everyone to have a great experience, regardless of their deploy size and the decisions that they make for their own builds. Simplistically, on our side, the work involved in building and serving content from a deploy can be looked at something like this. We get a lot of files. It could be as many as 1 million. We take that a lot of files, and we do a lot more work to process them, to store them, and to serve them. And 90% of the logic in that is covered by one collection. So I'm going to pause for a moment, because if you don't know whether or not you should laugh or cry or boo us for that, that's okay. Looking back, we are not quite sure how to feel either. And I want to take a minute to talk about that collection. That collection is actually a Merkle tree implementation. Merkle trees fundamentally are data structure trees where each non-leaf node is a hash of its respective child nodes. In our case, you can think of a non-leaf node as a directory and the leaf node as files. We use the tree structure here so that we can support larger deploys by splitting the structure of the deploy into multiple documents. We use Mongo, so for us, everything is considered a document. So there are multiple trees involved in the structure of a deploy. Merkle trees are also a good fit for identifying what we already have, so we can avoid storing it twice. For example, if we both run the same hello world build, we don't need to store the structure of that twice. Furthermore, large sections of a site don't actually change between deploys, and we can take advantage of this to have a shorter tree depth to improve performance. So now that we understand a bit the logistics behind it, let's look at what it actually does in more detail. So this particular collection, the tree collection, is used to resolve content for a web request. And it's also used to track file uploads and recursively parse the Merkle tree on every upload to update the leaf or the file node metadata. And then it also tracks when the deploy is finished by decrementing a counter that exists on that collection. So you might be thinking, okay, that's not great, that's a lot of work for just one collection, but if there's not that many trees involved in the deploy, chances are you're going to be fine. Well, turns out, yes, some deploys can be rather small and it works really well for them, but some deploys can be rather large and touch thousands and thousands of objects. In this case, this is just a graph over the last 24 hours, and one of the deploys touches as many as 23,000 trees. So that's quite a lot of documents to touch. So this collection becomes tree responsibilities and many problems. As we ramp up in size and consider the scale with concurrent deploys and concurrent file uploads, we would start seeing some problems. First, there's a lot of read-lock contention in MongoDB because you're repeatedly recursively querying the same documents to update file information. For larger deploys, this is far more punitive because determining if you're done is a lot more reads from the database. There's also a significant number of duplicated operations if you think of it, because we do the same operations for every file upload. For example, you have a file, you go recurse the tree, you find it, you update the size and other metadata. You do the same for the second upload and the 10th upload and so on and so forth. So it becomes, especially with upload concurrency, this decision becomes high risk. From an engineering point of view, the logic being so tightly coupled makes it really hard to reliably understand how deploys work, if not actually impossible. But the bigger issue is that it's also very, very difficult to validate assumptions and clarify problems that we need to solve, even on things that should be somewhat more known. So let me give you an example of that. Even quantitative questions like, what's the distribution of deploy depth? How many files were in a deploy versus new files? How often were we hitting past optimizations in the search tree? Crickets. So obviously, whenever we had to touch this area, we kept feeling very awesome about it. And it would be a lot of fun to troubleshoot an issue. So some problems were answered by asking the customers to just retry again. And retrying is not an acceptable strategy. We don't want that answer for our customers. We've decided the decision of reusing the tree for multiple operations is not only a performance issue, but also a stability issue. So it needed to be changed. We chose in the beginning to do less by reusing the tree, and that was a decision that outgrew us, and it was actually slowing us down. So let's look a little bit at how we broke that complexity. From a high-level overview, we could group the problems we were trying to solve with the tree collection in two categories. For resolving a request where the structure matters, the tree works pretty well. But we didn't have a good enough story, and it wasn't really a good fit for deciding when a deploy is down and tracking the deploy progress. We don't actually need a tree collection to decide any of that. We just needed the metadata to live somewhere. So we've burned it with fire and went back to the drawing board. We've decided to split responsibilities, try to split responsibilities in a way that would create more control over both areas. And we did that by introducing a new collection that will allow us specifically to keep metadata for every single file involved in a deploy, which would eliminate the read and write lock contention on Mongo, because every document would represent a single file rather a multitude. We could use better indexed queries to determine done. And we could also use all that metadata to rebuild the deploy structure in the end. Eliminating read lock contention meant Mongo was happier, and we could actually group together operations with less risk of impacting each other. The rest of the heavy work, which is recursively parsing the tree, was also reduced to one operation in the end, rather than updating it on every request. And because it's now independent, that means that making decisions like perhaps run it in a background worker for larger deploys are now more feasible. So now that we've had the strategy on how to represent the data better, we also looked at how and where this will fit into our system, if it should just replace existing functionality, or if it might be time to shuffle some things around. The deploy system is a tree node system, with the API doing all the heavy lifting and Netlify server being more of a proxy that uploads files to the cloud. We really didn't like the extra hop to the API and how lightweight Netlify server was. Our API is also overworked and underpaid, as it doubles as an origin server. So we were able to, just by looking at it, identify some potential pain points or things that weren't quite a good fit there. We've decided to avoid splitting file uploads because that work is related, and splitting it between Netlify server and the API doesn't quite make sense. And by moving file uploads explicitly on Netlify server, we can also actually eliminate the network latency on that extra call, plus reduce pressure on our API. And by not splitting related work, we are also making it easier on ourselves to track and understand the different stages of file upload request. So as I mentioned, we group all the file upload work logic in one service, leaving the API for control operations and actually finalizing the deploy, since it's the brain behind the operation and a much better fit for that. So that leaves us with a system that now has a clear scope and boundaries, which means it's a lot more straightforward for humans to reason about, and all the related logic is grouped together and can be addressed together in one go. So with the engineering bit done, now was time to test in production. And we are really fond of testing in production, and we do this usually by using feature flags. We dog food internally, and we're also able to enable a particular optimization for a percentage of live traffic through a gem called Flipper. So that allows us to have a more gradual, controlled rollout in production with live traffic rather than something that we control. And production is, well, where unknown bad things can happen. And it's a known fact that it's impossible to determine every single point of failure in a complex system at scale. And we've already talked a little bit about that. So when errors do happen, besides mitigating as soon as possible, it's also extremely important to not leave humans feeling powerless and feeling like they are unable to solve the problem and drive recovery. Outside of the system impact, the complexity of unknowns adds a significant overhead on humans, especially on incidents. So far, I guess we've talked about addressing complexity as a system level, so I want to take a minute to touch on it on the human side. One of the most relevant studies about humans and complexity happened mid-1990s by a researcher called Roy Baumeister, which is a social psychologist that wanted to understand the common day struggles, such as why do we feel mentally tired after working away at a complex problem. So he did so by taking 67 adults in a room that smelled like freshly baked chocolate chip cookies. Half of the study participants were allowed to eat the cookies, while the other half were prohibited from doing so. And just to add a little insult to injury, they were actually given radishes instead of the delicious cookies. After both groups finished eating, the participants were then asked to solve a seemingly apparently solvable but actually unsolvable problem. The radish eaters lasted for a little over 8 minutes and gave the problem 19 attempts. The cookie eaters, on the other hand, persisted for over 20 minutes and gave the problem 33 attempts. The study concluded that participants that had to make a tough decision or resist temptation to eat the cookie were depleted by their mental ability to solve complex problems, and that would make them give up on them that much sooner. While the other participants that were happy and refreshed, having eaten delicious cookies, were able to stay with it and recover that much faster. And we encounter this idea of recovery with athletes and when athletes talk about performance as well. And I think it's really interesting because performance has become this buzzword these days that is not only in systems, but it's also humans. Like, who would want people to perform better and feel refreshed and at 110% of mental capacity? And I actually find the idea of recovery and looking at how other disciplines approach recovery a more reasonable strategy than engineering for failure, because predicting failure is not always possible, but adding a strategy and guardrails and thinking about it in terms of recovery puts more emphasis on the human side of dealing with complexity as well. And how we recover is extremely important for our business as well, because when we fail, customers can't do business. Their sites are offline. So we want humans to feel confident mitigating an incident and allowing them time to recover mentally. Otherwise, we're all going to be just burned out zombies that are afraid of the systems we run, which is not cool, and it's quite a sad story. So I want to talk a little bit about engineering for recovery. Let me start by first giving you an example. I've told you earlier a bit about Netlify server. So in the beginning of the deploy performance work, we would toggle the feature flag on and off during a deploy based on some conditions. We tested it on a single node, then we tested it in the staging environment, deployed to production, tested on dog-fooded apps, and everything looked okay. After which, we've decided to enable it for a very small percentage of live traffic. It ran in production successfully for 2 hours, after which we started receiving reports that something might not be quite right. What ended up happening is one of the conditions would change the feature flag midway through the deploy, so that the deploy started using the new collection, but it finished in the old way. So the data was disconnected. Some of it was actually missing, and it ended up in an invalid state that wasn't affecting customers' live sites. It doesn't help that Netlify server is a multi-node system that has a local cache for validations and feature flags. So it was actually a poster child for potential race conditions, which is what happened during this incident. The good news is that by having a lot of control on our deploys through the work that we did, we were able to now reconstruct and fix deploys on the fly rather than having to restore from backup or ask builds to be retried. And a really strong motivation for introducing clear responsibilities and controlling your system and having control on how your data is represented for one purpose is what will allow you to fix problems like these more efficiently and be more efficient during outages. It's especially helpful to be able to reconstruct the data when you're dealing with low volumes. For example, 20% of the deploys are affected by this issue and they are left on a bad state rather than restoring from backup, which is notoriously slow. This is a much easier approach. Which leads me to my next point. Leaving data in an invalid state is a time-ticking bomb waiting for you. And defining what constitutes an incomplete or invalid state is mostly a known piece of information that can be tackled during development. Adding guardrails that prevent invalid states to happen will make the difference between getting the page at 2 a.m. and sleeping for 8 hours. So it's worth the time investment. But none of this control matters if we're not allowed to explore and have observable systems. We don't want to be effective only during outages. We want to be able to cater for future work as well. So the last point we addressed before calling it done was to attempt to improve the observability of our system. And there was some good news, but there were some things that didn't work quite right. We already have structured events, structure your events, but we did not have an aligned structure between those three services. We had a really good log aggregator, but we had no way to get answers in just one search because the structure wasn't aligned. We had a lot of data about everything. But it needed to be human interpreted. It wasn't in a form that was able to be really effective on its own. So what we really doubled down on is identifying those pain points and having a unified event structure across our services to be able to connect our data and use it to ask questions and paint a story with minimal human cognitive power. So data that tells a story is actually what is useful in exploratory work, in technical plans, in troubleshooting. And if data doesn't tell a story, it just becomes noise that adds a lot of overhead. So in the end, I want to go through some of the strategies and lessons learned that have worked for us and that we've discussed throughout this talk. We talked about how complexity can sometimes be necessary and introduce stability. We've talked about the benefits of mitigating known points of failure early on. We talked about splitting responsibilities in order to create more control. We talked about grouping related work. We talked about avoid doing heavy work until the end. We talked about prioritizing recovery and how important that is for both systems and humans. And we talked about making sure that the data tells a story. If you want to read more about the deploy performance work and all the nitty-gritty details about testing and how we made some of our decisions, there are 2 blog posts where we talk about this that I have linked in this slide. And with that, I can't wait to hear some of your experiences and thoughts. Thank you.